This is example 10.2 from Discovering Design with Chemistry. The first problem says a gas expands under constant pressure. If it has a volume of 2.12 liters at 25 degrees Celsius, what is the temperature in degrees Celsius when it has reached a volume of 5.09 liters? So the first thing that you can probably guess is that we're going to use the equation that we just recently learned in the text before this example. The thing that we have to remember is that temperature always has to be in Kelvin. So any temperatures they give us or they want, we're going to have to convert to or from Kelvin. So let's look at our different things. We have a volume listed here. We're going to call this volume 1 because that's our first volume. Here's our temperature 1. And then it mentions that it's under constant pressure, which means the pressure doesn't change from situation 1 to situation 2. So we can just cross these out because they're the same. And then it asks about the temperature. What it actually wants is the temperature at the end. So the T2 is what we're asking for. And then they give us a volume. So this is the volume in the second situation. So let's go ahead and convert our temperature to Kelvin so that we're ready to work with it. So we have 25.0 degrees Celsius plus 273.15. Now in adding and subtracting, we have to remember that our 25 has its last digit in the tenths place, and so that's where our precision is going to end. So we're going to have to round this after we add it. So that becomes 298.2. And that's Kelvin. There's no degree symbol with the Kelvin scale. So now we're ready to start plugging things in because our volumes are both in liters. That's great. And now our temperature is in Kelvin. So let's plug stuff in. So we have, actually, let's go ahead and solve for the thing that we need. This is the thing we're looking for. So let's take our equation and let's move it around so that things are already where they need to be. We're going to move think of it like if you've done the butterfly thing in algebra, where you have the thing that's on the bottom show up on the top on the other side. And then we're going to divide both sides by the volume that we don't want to be over there. So this is what we're going to use to find our answer. So we're going to say T2, that's our final temperature when we've changed the volume. And we're going to plug in for V2 5.009 liters. And our temperature 1, we've converted. I should probably have labeled that. So this is our T1 over here. So 298.2, that's in Kelvin. And then we divide that by our volume 1, which is 2.12 liters. So 5.09 times 298.2 divided by 2.12. Now, 3 significant digits is where we're going to have to cut this one off, and so this becomes 716. So our temperature is 716 Kelvin. Now, does that answer the question? No, because it asks for our temperature in degrees Celsius. So we're going to take the Kelvin scale equation formula thing, and we're going to plug our answer in. We can also go ahead and rewrite this one if we want so that it's already solving for what we want, and then plug it in. So 716 minus 273.15, and because we're adding and subtracting now, we're not counting the number of significant digits. Instead, we are just taking it to the least precise one, which is the ones place here. So that means 443. So this is 443 degrees Celsius. Wow, that's hot. All right, so the second one, because there's a part 2, not a part 2 to the question, but a part 2 to the example. The second one says, a weather balloon is filled with a volume of 45 liters of helium at 1.02 atm and 22.4 degrees Celsius when it reaches an altitude of 3,000 meters. Now, we haven't talked about altitude yet, so you can know that this is not a significant part of the question because we haven't talked about altitude at all in this course. It experiences a pressure of 0.692 atm and a temperature of 4.50 degrees Celsius. What is its volume at that altitude? So let's start labeling things. So we have an initial volume, so this will be V1. This is 45.0 liters. And then it gives a pressure here, so this is our P1. And then it gives a temperature. So this is our T1. Now, it's not in the right unit, but that's okay. We know how to convert it. So let's go ahead and list these. Let's go ahead and add so that we can convert this to Kelvin. Alright, so 22.4 had its last digit in the 10th place, so this is going to be 295.6. That's Kelvin. Alright, let's keep rereading our question, looking for more. So when it gives up, the altitude is just telling you that there's a change here. We don't need to worry about what this number is. It experiences a new pressure. So here's our P2 and a new temperature. Here's our T2, and our volume is actually what the question is asking. This is what we want to know. So our V2 is the question. Our P2 is 0.692 atm, and then our second temperature is 4.50 degrees Celsius. And again, we know that we have to put everything in Kelvin to use these, combine any of the gas law equations. And so let's go ahead and convert that. So 4.50 plus 273.15. And this one we actually have to keep both decimal places because the 4.50 had 2 decimal places. So that'll be 277.65 Kelvin. Alright, so let's write our equation that we're working with. So we have PV over T equals PV over T. And before we start plugging these in, I'm going to go ahead and rearrange this. So this will get multiplied by both sides on the top, and this will get multiplied or divided on both sides on the bottom. So now we're ready to fill it in because these have canceled out. So we can solve for V2. Alright, so our first temperature is 277.65 times our first pressure, 1.02, times our first volume, divided by our second pressure, and our first temperature. So our units cancel here, and here, and here, and here. So we're left with just the liters that we want. Alright, so of all these numbers, we had 3 significant digits as our least number of significant digits, so we'll end that with 62.3 for our liters. And that's what they asked, was for volume. So we're done.